Somewhere above you tonight, there is a star that may not exist. Not a faint one, not a hidden one of the brightest in the sky. You have looked straight at it. You may have been looking at nothing. We call it Betelgeuse. 600 light-years away, or 700. After 4 centuries of measuring, we still cannot agree, which means the light arriving tonight is 600 years old. Whatever has happened to that star since has not reached us. It could still be burning. It could already be gone. There is no way to check, and there will not be for another 6 centuries. You are not seeing a star. You are seeing a message about one, and the message is old. Now look at the rest of them. Every point up there is the same kind of thing. All of it old. All of it a report from somewhere that has already moved on. Nothing you see in that sky is happening now. You are watching history arrive. And this is the part that is harder to shake. Everything you know about your own life is the same kind of object, a pattern in your brain, a photograph, a scar. All of them exist right now. None of them is the past. Each one is only a claim about a moment you cannot go back and check. You have never once touched your own history. You have only ever held records of it. So this is what the next hour is about. And it is not a question about feelings. Is there anything in physics, anything at all, that makes a real past more likely than a convincing record of one? For 100 years, there was a good answer. Everyone accepted it and stopped looking. In December 2025, 3 physicists took that answer apart. What they found underneath was not a fact. What physicists found underneath was not a fact, it was a circle. A drop of ink enters a glass of water. It spreads, it thins, it reaches the walls, and after a while the water is uniformly gray, and it stays that way. Nothing you could do to that glass would gather the ink back into a bead, not shaking it, not cooling it, not waiting. You could sit with it for the rest of your life. And when that same footage runs in reverse, you know immediately. Not by reasoning, you do not consult an equation. Gray water drawing itself into a single dark point is wrong in a way a child can see from across a room. That recognition is the only reliable instrument a human being has for detecting the direction of time. And out of everything physics has ever written down, exactly one law agrees with it. So look closer at the ink, because the obvious answer is not the right one. Follow a single molecule. It drifts, it strikes a water molecule, it changes direction. Watch that one collision, then watch it in reverse. There is no test you can run to tell which version came first. Both obey the laws of motion perfectly. Both are legal. Do it again with 2 molecules. Same result. 10, 100. At the level of individual pieces, nothing in that glass has any preference about which way time runs. Every interaction inside it is a 2-way street. The irreversibility is not in the parts. It appears only when you stop tracking parts and start counting. Here is the count that matters. Take every possible way the ink molecules could be positioned and still leave the water looking evenly gray to your eye. That number is astronomically large. Now take every possible way they could be positioned to leave a tight dark bead sitting in clear water. That number is also large, but set beside the first, it is nothing at all. The ink does not spread because something drives it outward. It spreads because there are unimaginably more ways to be spread than to be gathered. Every arrangement is equally permitted. There are simply far, far more of one kind. And the word unimaginably is doing real work. Shrink the problem until it is almost trivial. 100 particles in a box, and you want to catch all of them, by chance, in the left half. Check once a second, starting at the beginning of the universe, and you would still be checking 3 trillion times its present age from now before you should expect to see it once. That is 100 particles. A single breath holds over 1,000 billion. Nothing forbids the ink from gathering itself. The arrangements that do it are simply so rare that the universe has not lasted long enough for them to matter. This is what entropy actually is. The word arrived in 1865 from a German physicist named Rudolf Clausius, and it did not come from philosophy. It came from machines. Engineers building steam engines had noticed something stubborn. You could turn heat into work, but never all of it, and never without loss. Something was always wasted, always in the same direction, and no amount of engineering skill could recover it. Clausius gave that one-way leakage a name. Almost everyone is then taught the wrong definition. Entropy is not disorder. It is not decay or chaos or a substance that accumulates. Entropy is a count. It measures how many microscopic arrangements would produce the situation you are looking at. Rare arrangement, low entropy. Common arrangement, high entropy. That is the whole of it, which exposes the deepest misunderstanding about the law built on top of it. The second law of thermodynamics is not a force. Nothing pushes entropy upward. There is no field, no pressure, no hidden tendency inside matter that drags systems toward disorder. The ink does not want to spread. It has no preferences at all. Gravity acts, magnetism acts. The second law only counts. Systems are found in common arrangements because common arrangements are common, and that is the entire mechanism. It is the one major law of physics that is, at bottom, bookkeeping. There is a subtlety here worth pausing on because it becomes important later.
Entropy is a count. An account requires a decision about what is being counted. Gray water looks uniform, so billions of distinct molecular arrangements are grouped together and treated as a single situation. That grouping is what makes the number enormous. Be exact about what this does and does not mean. The molecules do not behave differently because someone is watching them. Nothing physical changes. What changes is the accounting. Entropy is a property of the description we have chosen and of how coarse that description is, and the equations do not hand us that choice. So the line between arrangements we treat as identical and arrangements we treat as distinct is drawn from outside the physics. Remember that. It comes back. Now turn it inward, because you have been living inside this law your entire life. You do not feel entropy. You feel time passing. There is a strong case that these are one fact viewed from two positions. Ask what actually makes the past feel unlike the future. You hold information about one and none about the other. Causes come before effects and never after. Heat leaves your coffee and never returns to it. Every one of those asymmetries is the same asymmetry, and each traces back to that ratio of counts. Which is an uncomfortable thought to hold steadily. The forward motion of your own life, the most immediate and undeniable thing you have ever experienced, may not be a property of time at all. It may be a statistical slope, and you are standing on it, facing downhill. Step outside and the same slope is written across everything. A star pours light into the dark and never draws it back. Heat crosses from hot to cold and never reverses. Every process visible in the sky, at every scale,
runs one way and only one way. The universe is the largest clock ever assembled, and nothing in it has ever been observed to tick backwards. Not because reversal is forbidden, because out there, the counting has become absolute. Which leaves one word. It is the most important word in this film. Almost. Entropy almost always increases. You almost always find common arrangements. The ink almost never gathers. Every sentence in this law, without exception, is a statement about probability, and probability has no locked doors. It has only doors that are extraordinarily unlikely to open. So the direction of time is not a wall, it is a slope. Steep past any power of imagination, but a slope. And a slope can be climbed by luck alone. For most of the 19th century, that was a technicality, an asterisk on an otherwise flawless law, and nobody thought it needed attention. Then, in 1872, a physicist in Vienna set out to prove the second law from the motion of particles and nothing else. He succeeded. His proof is still taught today, and in the century and a half since, nobody has found an error in the mathematics. The error was never in the mathematics. Before he wrote a single equation, he had assumed something about the past. It was such a small assumption, and it seemed so obviously true that he never noticed making it. 4 years later, a colleague noticed. Vienna, 1872. A 28-year-old physicist is about to explain why time runs in one direction, and he intends to do it using objects that most of his colleagues do not believe exist. Atoms. It is hard now to recover how open that question was. There was no image of an atom. Nobody had seen one, isolated one, or measured one directly. A serious school of thought held that atoms were a convenient fiction, a bookkeeping trick for chemists, and that any physics built on invisible particles was a physics built on faith. Ernst Mach, among the most formidable minds in the city, spent years pressing that point. If you cannot observe it, do not build on it. Ludwig Boltzmann built on it anyway, and he built the largest thing anyone had attempted with it. His target was the second law of thermodynamics, not to observe it, not to assume it, to derive it from nothing but particles in motion and the ordinary laws of mechanics. What he produced is called the H-theorem, and it is one of the boldest calculations of the 19th century. He found a quantity inside a gas, called it H, and proved using nothing but collisions and Newton's laws that it could do exactly one thing. Fall. Not usually fall, not tend to fall. Fall. So long as the gas kept colliding with itself, the number could only go down, and once it reached bottom, it stayed there. Flip the sign, and that is entropy climbing, which meant the one-way behavior of heat, the thing engineers had been cursing for half a century, was not an extra law bolted onto mechanics from outside. It was a consequence of mechanics. It fell out of the collisions. Boltzmann had taken the direction of time and grounded it in the motion of invisible particles whose existence half his profession disputed. The mathematics was correct. It is still correct. But somewhere inside the derivation sits a line that has to be there for the proof to work, and it is not a law of mechanics. Before any two molecules collide, Boltzmann assumed their motions were unrelated. No coordination between them. No conspiracy. each arriving with no trace of anything the other had ever done. In German, the clause is called the Stoßzahlansatz. In English, it is usually softened into the assumption of molecular chaos, which makes it sound like a description of the gas. It is not a description. It is a stipulation about what came before. And it is the single element in the whole derivation that does not work equally well in both directions of time. Molecules arriving at a collision uncorrelated is entirely reasonable. Molecules leaving a collision uncorrelated is not, because the collision has just linked them together. The assumption is only true facing forward. Boltzmann had put the arrow of time into his proof by hand on the first page in a clause so mild it read like housekeeping. He did not see it. Nobody else did either for 4 years. Then Joseph Loschmidt read it. Loschmidt was more than 20 years older, also in Vienna, a colleague and a friend. The objection he raised in 1876 takes a sentence to state and has never been fully answered. Take a gas, let it run. Let H fall, exactly as the theorem promises, until the gas is thoroughly mixed. Now reach in and reverse the direction of every particle at once. Nothing else changes. Same positions, same speeds, every velocity flipped. That configuration is legal. Nothing forbids it. It is a state a gas is permitted to be in. And from there, the gas will retrace its own history. It will unmix. H will climb. Entropy will fall, step by step, all the way back to where it started, and every collision on the way will obey Newton perfectly. Which means the theorem cannot be the thing Boltzmann believed he had proved. You cannot pull one-way behavior out of two-way ingredients. If an arrow comes out of the proof, the arrow was in the ingredients. It was. It was sitting in that mild clause about molecules arriving unrelated. Loschmidt had shown that molecular chaos does not follow from Newtonian mechanics at all. It has to be assumed. And assuming it means assuming something about the past. Boltzmann's response took him the better part of 20 years, and it changed physics permanently. He gave up certainty. The second law, he eventually argued, is not a law in the way gravity is a law. It is not something the universe is incapable of breaking. It is something the universe is overwhelmingly unlikely to break. Loschmidt's reversed gas is real and permitted, and would genuinely run backwards. It is only that among all the states a gas can occupy, those that behave that way are so scarce you will never meet one. This is now the standard view. Every physicist alive is taught the second law this way, and it saved the theory. It also opened a door that has never since been closed. In 1896, a young mathematician in Berlin named Ernst Zermelo pushed on that door. Zermelo had been reading Henri Poincaré, who a few years earlier had proved something about closed systems. If a system has finite energy and finite space, then given enough time, it must return arbitrarily close to any configuration it has ever occupied. Not roughly, arbitrarily close, and not once, but endlessly. Apply that to a gas and the consequence is unavoidable. Wait long enough and the ink comes back out of the water. Wait long enough again and it happens again. Entropy does not merely dip, it returns all the way down, over and over, without end. Boltzmann's reply was the only one available, and it was right. The waiting times are so vast as to be physically meaningless. For anything the size of a room, the recurrence interval dwarfs the age of the universe by margins that cannot usefully be written down. True, and beside the point. Because Zermelo had not asked how long, he had asked whether. In the space between those two questions, the whole of this film is waiting. Follow what Boltzmann had conceded. Entropy can fall. Rarely, absurdly rarely, but by nothing more than luck, a system can arrange itself into a state of far lower entropy than its surroundings. Now notice what a low entropy state actually is: rare, structured, specific, improbable. A memory is matter, arranged in an extraordinarily unlikely way, which places it, statistically, in the same category as every other improbable arrangement in the universe. So is a photograph. So is a geological layer, a fossil, a written page, a mind holding a childhood. Every record that has ever existed anywhere is a low entropy configuration of matter. And Boltzmann had just established that low entropy configurations do not require a history in order to exist. They only require luck. He spent 30 years grounding the direction of time in statistics. In doing it, he made every trace of the past, everywhere in the universe, into something that could in principle have arrived from nothing. Boltzmann died in 1906 at 62 while on holiday near Trieste. He did not live to see atoms confirmed or his statistical picture become the foundation of modern physics. Both arrived within a few years of his death. There is one more thing he left behind, and it is not in the H theorem. Late in his life, he had followed his own argument to the end. He asked what the universe would have to look like if entropy statistics were taken completely seriously, and then he wrote the answer down. It is the strangest idea a physicist has ever put into print, and everything after this point is about what happens when you take it seriously. A sealed box, left alone. Whatever is inside it mixes. Hot regions cool, cold regions warm. Gradients flatten, structures come apart. Given long enough, the contents arrive at a condition in which nothing further happens. Nothing flows because there is nowhere left to flow. Nothing changes because every difference has been evened out. Physicists call this thermal equilibrium. It is the most featureless condition matter can occupy. No shapes, no patterns, no events. A system that has finished. And here is where almost everyone's intuition fails. Equilibrium is not stillness. The particles in that box have not stopped. They are moving as fast as they ever were, colliding as often as they ever did. What has ended is the net motion, the systematic drift from one place to another. Underneath, the shuffling continues, and it continues forever. Which means the statistics never switch off. At every instant, that box is landing on one particular arrangement of its contents. Almost all of those arrangements look identical from outside, mixed, featureless. But not every arrangement does. Occasionally, by nothing more than the arithmetic of chance, the shuffling produces something that is not featureless. A patch briefly hotter than its surroundings. A region where the particles have wandered into a formation. A momentary structure appearing inside a system that has no structure, and then dissolving back into the mix. These are called fluctuations. They are not exotic. They are not a loophole. They are the direct and unavoidable consequence of a system built from parts that never stop moving. Equilibrium is not the absence of events. It is the absence of a direction. In 1895, Boltzmann took that fact and pointed it at the universe. He was 51, and he had spent 20 years defending statistical mechanics against people determined to dismantle it. In a short letter to the journal Nature, he set out an answer to a question almost nobody had properly asked. If entropy statistics are correct, why is the universe we live in so far from equilibrium? Look at it. Stars burn. Matter is gathered into structures. Heat flows. Differences exist everywhere, at every scale. This is not a mixed, featureless cosmos. It is an extraordinarily ordered one, and by the accounting of his own theory, that is not what we should be finding. His answer, an idea he credited to a former assistant, was to invert the question. Perhaps the universe as a whole is at equilibrium. Perhaps it has been for a span beyond description, and will be for a span beyond description more. Mixed and featureless across almost all of its extent and almost all of its duration. And perhaps the region we inhabit is a fluctuation, not created, not designed, not begun, deviated into existence in the way a hot patch appears inside a sealed box, and destined to dissolve back the same way. We would find ourselves inside an ordered region for the plainest possible reason. Observers cannot exist in the featureless parts. That sentence is carrying a great deal, and it is worth being exact about it, because this is where the idea stops being a curiosity. Boltzmann was not arguing that the universe is improbable. He was arguing that we occupy a rare place, and that there is no mystery in finding ourselves there, because the commonplaces contain nobody to do the finding. And given unlimited time, an equilibrium system does not merely revisit states it has held before. It reaches every arrangement its parts are permitted to take, every one of them. Not because anything is driving it there, but because it has forever, and forever is sufficient. Which raises the question this entire film turns on. How large a fluctuation does it take to make you? The mathematics is brutally unforgiving here. The probability of a fluctuation does not fall in proportion to its size. It falls exponentially with the amount of order involved. That distinction is everything. If a fluctuation twice as large were merely half as likely, none of this would matter. It is not half as likely. Enlarging a fluctuation does not reduce its probability. It reduces it by a power, and each additional increment of order costs another exponential factor, and the exponents stack without limit. The overwhelming majority will be the smallest ones that can manage it, not because small ones are favored, because large ones are penalized so severely that they stop competing altogether. Now set two candidates beside each other. The first is the universe you believe yourself to be in. 13.8 billion years of ordered history. Hundreds of billions of galaxies. Every star, every world, every atom of your body, positioned by a real sequence of physical events reaching back to a beginning. The second is much smaller. A single region, briefly ordered, containing nothing but the physical state that constitutes one moment of your experience. The pattern in your head as you listen to this, the sense of a room around you, the feeling of remembering a childhood. Nothing else at all. No earth, no sun, no history. Only the configuration required for this one instant to be occurring, holding together for a moment, and then coming apart. The second requires an almost inconceivably smaller departure from equilibrium than the first, and by the exponential accounting we have just walked through, the second is not slightly more probable than the first. It is more probable by a margin that cannot be written in ordinary notation. Every scrap of evidence you have for the large universe sits inside the small one. Every memory, every observation, every measurement anyone has ever written down. The small fluctuation does not need to counterfeit anything because the evidence is nothing more than the arrangement, and the arrangement is what fluctuated into being. There is no experiment that separates them. Both options predict exactly what you are experiencing right now. Physicists have a name for the thing in that second scenario. They have had one for over a century, and they use it with a certain discomfort because naming it does not help. They call it a Boltzmann brain. The man who rooted the arrow of time in probability, who surrendered certainty to save his own theorem, and who proposed that our whole ordered corner of reality might be a passing accident, has his name fixed to the most unsettling consequence of the idea. It is not a brain in a jar. Nobody is doing this to you. There is no experimenter, no simulation, no deception of any kind. Only an arrangement of matter, entirely permitted by the laws of physics, that happens to be having your exact experience for as long as it holds its shape. One caution before we go on, and it is not a small one. Nothing here claims that this is happening. Nothing here says it is likely tomorrow, or in a lifetime, or within any span of time that means anything to a person. Every step is a statement about which of two improbabilities is less improbable, and that is a far narrower claim than it becomes when it is quoted badly. What the argument does say is harder to put down. Given equilibrium, given unlimited time, and given nothing but the statistical reasoning that every working physicist accepts, the cheapest way to produce an observer is not to produce a universe. It is to produce the observer. For 100 years there was an answer to this, a good one, quantitative, reassuring, and repeated so often that it stopped being examined. That answer is the next thing to come apart. The reassurance is a number. It has been offered for more than a century, in lectures and textbooks and letters to journals, and it has always worked. Whenever the fluctuation argument surfaces, somebody produces the number and the room relaxes. The number is a waiting time. Work out how long you would have to sit beside a universe at equilibrium before a fluctuation of the necessary kind appeared. The answer is not large the way cosmic distances are large. It is large in a way that breaks the notation. The age of the universe is not a rounding error against it. The age of the universe does not register at all. So the reply is simple, and it sounds decisive. The event is so rare that it will effectively never happen. File it with the mathematically permitted and the physically irrelevant, and get on with the work. For 100 years, that is exactly what happened. The trouble is that it answers a question nobody asked. Nothing in the fluctuation argument ever claimed the event was likely. Not once, anywhere. The claim was comparative. Set the fluctuation beside the alternative and ask which of the two is less unlikely. Both are absurd. That was never in dispute. A universe arriving with 14 billion years of ordered history ahead of it is a fantastically improbable object. A momentary arrangement holding one observer's experience is also fantastically improbable. The question is which of those two absurdities the mathematics prefers, and you cannot answer a comparison by describing one side of it. Telling someone the fluctuation is vanishingly rare is not a rebuttal. It is a restatement of the premise. Everyone had already agreed it was rare. The argument was that the thing you believe instead is rarer still. Which means that for a century, the standard reply has not been defending the ordinary account of the past. It has been changing the subject. So what has actually been holding that account up? One assumption. It has a name, and the name is recent. It was given in the year 2000 by the philosopher of physics David Albert. He called it the past hypothesis. It states that the universe began in a condition of extraordinarily low entropy. Not that it evolved into one, not that it was driven into one, that it started there as an initial condition inserted at the beginning by hand. This is not a derived result. Nothing in mechanics produces it. Nothing in thermodynamics demands it. It is an extra postulate, bolted onto physics because without it, the second law does not function, and with it, everything falls into place. Every argument you have ever heard about why memories are reliable, why records can be trusted, why the past is fixed while the future is open, is standing on that postulate. Take it away and the whole structure loses its floor. Now look closely at what the past hypothesis is actually claiming, because on its face it sounds wrong. The early universe was smooth. Everything we can reconstruct about its first stages describes matter spread out with extraordinary evenness. No clumps, no structures. Almost no variation from one region to the next. And smooth should mean high entropy. Evenly mixed is the boring arrangement, the one there are countless ways to build. If the universe opened smooth, it should have opened at the top of the scale, not the bottom. Except that reasoning has left out gravity. Gravity has no interest in evenness. Every piece of matter pulls on every other piece. The pull never switches off, and it has no opposite. There is no repulsive version of gravity to balance the books, which means that for matter under its own weight, the counting inverts completely. Spread out uniformly, a cloud of gravitating matter sits in a fantastically special arrangement. Almost any disturbance sends it falling together. Clumped is the ordinary condition. There are vastly more ways for matter to be gathered into knots and filaments and lumps than for it to hang in perfect uniformity. So smooth is not the high entropy state. For a universe full of gravitating matter, smooth is the extraordinarily ordered one, which turns the history of the sky inside out. Every galaxy formed by matter falling together. Every star lit when a cloud collapsed under its own weight. Every planet, every rock, every atom in your body was drawn out of a diffuse spread and packed into a knot. All of that gathering, all of that structure. Every point of light you have ever looked up at.
Entropy going up. The night sky is not the universe becoming ordered. It is the record of the universe coming apart from an order it began with. That vast cosmic architecture, the filaments and clusters and spiral arms, is the wreckage of something arranged far more precisely than anything now inside it. Roger Penrose once tried to put a figure on how special that starting condition was. His estimate was 1 part in 10, raised to the power of 10, raised to the power of 123. A number that cannot be written out in full because there is not enough matter in the universe to write it on. And nobody knows why it started that way. This is not a gap that gets filled next year. It is the largest unexplained assumption in physics. We can measure the smoothness. We can trace its consequences forward with extraordinary precision. What we cannot do is say why the universe opened in a condition so improbable that everything since has been a descent away from it. The past hypothesis is not an answer. It is a placeholder with a name, sitting exactly where an answer should be. And it is the only thing standing between you and the conclusion of the last chapter. There is a serious modern objection to that conclusion, and it deserves to be put properly. In 2014, Kimberly Boddy, Sean Carroll, and Jason Pollock argued that the fluctuation scenario carries a hidden mechanical assumption of its own. Fluctuations require something to be happening. A system that shuffles must have internal dynamics, states turning into other states, a process in motion. Their claim is that a universe which has genuinely finished changing does not shuffle at all. It is not mixing slowly. It is not producing rare arrangements infrequently. It is doing nothing whatsoever. On that reading, equilibrium is not a lottery with astronomically long odds. It is a lottery that has stopped drawing. And a fluctuation cannot be improbable if it is impossible. The reply is Zermelo's, returning after 80 years and aimed this time at the rescue rather than the theorem. If the number of states available to the universe is finite, it cannot be genuinely static forever.
A finite system with unlimited time must revisit and reshuffle. The recurrences come back, and the fluctuations come back with them, which is where the matter sits today. Not settled, not close to settled. Two camps, both serious and both competent, arguing over whether a particular kind of nothing can produce a particular kind of something and how often it manages it. Now notice what every one of those arguments has in common. Every single one is an argument about probability. How likely, how rare, how long, how many. For 130 years, the entire dispute has been conducted in the language of odds. In July 2025, 3 physicists asked a different question. Not how likely, what the argument is standing on. In July 2025, a paper appeared on the public server where physicists post work before it has been reviewed. It contained no experiment, no observation, no new data of any kind. It reported no discovery about the universe. Its subject was an argument about the universe and whether that argument had ever been properly built. There is something disorienting about a paper like this. Physics normally advances by finding a new thing in the world. This one advanced by finding an old thing in the reasoning. The title was long, and it named 3 subjects nobody had thought to name together: disentangling Boltzmann brains, the time asymmetry of memory, and the second law. That December, it was published in the journal Entropy. 3 authors, Jordan Scharnhorst, David Wolpert of the Santa Fe Institute, who has spent a career on one narrow and difficult question: what a physical system can and cannot know about the world it is sitting inside. And Carlo Rovelli. Rovelli is among the small number of living physicists whose name travels outside physics. His research is in quantum gravity. He has also written about the nature of time for more than 1 million readers in over 50 languages. When he attaches his name to a claim about time, it is not a casual act. None of the 3 set out to tell you your memories are false. That is worth establishing early because this paper is very easy to misreport. What they set out to do was narrower and considerably more dangerous. They set out to find where the argument was anchored. To do that, they first had to build a model of the thing everyone had been arguing about, and build it in a very particular way. Recall what went wrong in 1872. That proof failed not because the mathematics was faulty, but because a direction of time had been inserted at the outset, quietly, in a clause about what came before. The arrow came out of the proof because somebody had put it in. So the first thing these 3 did was construct a description with no arrow in it at all. They treated the entropy of the universe as a random process, not a fixed history, but a quantity that moves according to probabilities. And they imposed 2 conditions on it, deliberately. The first condition: the process must be time-symmetric. It runs identically in both directions, with no preference whatsoever for past over future. Nothing smuggled in. The second condition: it must be time translation invariant. No moment is special. No instant is privileged over any other. The rules are the same at every point along the line. They called the construction the entropy conjecture. It is, in a sense, the honest version of Boltzmann's project. Everything he assumed by accident, they refused to assume at all. And then they asked what conclusions a model like that can actually support. The answer was almost nothing. The reason is a technical point that turns out to be devastating. A random process on its own does not tell you what is happening. It tells you only how things change. To extract any actual statement from it, you have to give it a foothold. You have to say, at this moment the quantity had this value. Then the mathematics will tell you what to expect on either side. The term for supplying that foothold is conditioning, and every argument about entropy that anyone has ever made requires it. Here is what the three authors established. The physics does not tell you which moment to condition on. Not that the choice is difficult. Not that we lack the data to make it well. The process itself contains no instruction of any kind about which instant should be held fixed. It is time translation invariant, which means every moment has an equal claim, and none has a better one. So the choice has to arrive from outside the mathematics. It is an assumption made by the person doing the reasoning, and it cannot be derived from anything. If that shape feels familiar, it should. You have met it twice already. Once in a clause about molecules arriving uncorrelated. And once when the counting turned out to depend on a decision about which configurations to lump together, a decision the equations never make for you. This is the same move again, at the deepest level it has yet appeared. Now follow the standard argument and watch where the conditioning happens. Ask why you should trust your memories. The answer is that the second law of thermodynamics guarantees records are reliable traces of a real past. Ask why you should trust the second law. The answer is that we observe entropy increasing, everywhere, without exception, and have observed it for as long as we have kept records. Read those two answers again, side by side. The reliability of memory is justified by the second law. The second law is justified by the reliability of memory. The premise is standing on the conclusion. The conclusion is standing on the premise. There is no third thing underneath, holding either of them up. That is not a subtle flaw, and it is not a philosopher's objection shouted from the sidelines. It is a structural fact about the argument, demonstrated formally by three physicists using a model built specifically to make the structure visible. Now be precise about what has and has not been shown, because this is where the work gets mangled. They have not proved you are a fluctuation. They have not proved you are not. They have not shown that your childhood failed to happen, and they make no claim at all about what is true. What they have shown is that the argument against the fluctuation and the argument for the ordinary past share the same defect. Both require a conditioning choice. Neither can justify its own. And each has been in the long habit of borrowing its justification from the other. It is a diagnosis, not a verdict. The paper does not hand you the answer. It tells you the question has been badly formed since the 1890s, and that everyone on every side has been forming it that way. There is one further consequence, which the authors state plainly and which almost nobody quoting this work has noticed. The same circularity reaches experimental data. Every measurement ever taken is a record, a reading, a plate, a stored file, a number in a notebook. Its reliability rests on precisely the same assumption as the reliability of your memory, because it is precisely the same kind of object. Which means the circle does not merely enclose your childhood, it encloses the evidence for the second law. It encloses the evidence for every law. Every observation ever made in the history of science is a low-entropy arrangement of matter, trusted on grounds that cannot be established without first trusting it. There is no experiment that gets you out, because an experiment is the thing in question. Which leaves the problem the next chapter has to face. If the argument against the fluctuation is circular, then what is the argument for the ordinary story? For the real childhood, the real Earth, the real 14 billion years? There is one. It has been the foundation of physics since the 19th century, and hardly anyone has ever examined its shape. It has the same shape. Every argument about the past begins by choosing a moment. Not consciously, nobody announces it. But somewhere near the start of the reasoning, one instant gets nominated. Its condition gets treated as given, and everything else has worked out from there. In this story, there are two candidates, and only two. The first chooses now. It takes the state you are in at this instant, the arrangement holding your experience together, and treats that as the fixed point. Then it reasons outward and asks what most cheaply produced it. The second chooses the beginning. It takes the early universe in its condition of extraordinary order and treats that as the fixed point. Then it reasons forward, and everything follows. Entropy climbs, structure forms, records accumulate, you get a history. That second choice is the past hypothesis. It is the one you have been living inside your entire life, and it is the one every physics course in the world teaches without ever mentioning that a choice was made. Now hold the two of them up together and look for the difference. Both nominate a single moment and hold its value fixed. Both reason outward from it using identical statistical mechanics. Both are consistent with every observation you have ever made, and with every observation anyone has ever made. Neither is derived from anything. The difference between the ordinary account of your life and the most disturbing idea in physics is not a difference of evidence. It is not a difference of rigor, or of mathematics, or of care. It is which instant you decided to nominate. The three authors state the consequence in one line, and it is the most quietly devastating sentence in the paper. In this respect, they write, the Boltzmann brain hypothesis and the second law are equally legitimate. Then they add two words in brackets, or not, because the argument cuts in both directions. If neither conditioning choice can be justified, the conclusion is not that both hypotheses are respectable. It is that neither has earned the standing we have been granting one of them for 2 centuries. It is worth asking why one of them feels obviously correct and the other feels like madness, because that difference is not in the physics. You were raised inside one of them. Every book, every lesson, every conversation you have ever had assumed the second choice, which is why the first arrives sounding like a provocation rather than an alternative. That reaction is real, and it is worth noticing. But familiarity is not a form of proof, and the mathematics is entirely indifferent to which option you find comfortable. The paper contains a third option, and it exists to close the easiest escape route. Most people, on hearing the fluctuation argument, reach for the same objection. A lone arrangement holding one moment of experience is too fragile, too thin. Surely it would come apart immediately, and surely a real person inside a real world is a more robust thing than that. So consider a version in which the fluctuation is not small. Nominate a moment 1,000 years ago. Condition on that instead. The hypothesis is now that the world fluctuated into existence in roughly the year 1000, complete and already running. Oceans, continents, a fossil record in the rock, light already in transit from distant galaxies. Everything apparently older than that instant is not the trace of an event. It is part of the arrangement that arrived. The mathematics is unchanged. Only the nominated moment has moved. And the same question applies. What tells you which instant to condition on? Nothing does. That is the whole of the finding, which brings the problem somewhere it has not yet been, and this is the part that should change how the sky looks to you. Everything we know about the history of the universe is a claim about records, not as a metaphor, literally. Nobody has ever observed the past of the cosmos. We observe light arriving now and reconstruct a history from it. A galaxy in a deep field is not a distant object being watched. It is a pattern of energy landing on a detector this morning, from which a story about 10 billion years ago is assembled. A telescope is not a window. It is a memory device, the most sensitive one ever built, and the same kind of object as everything else in this film. Right now, light is crossing the space between here and objects nobody has ever seen. Some of it departed before the Earth existed. Some will not arrive for another 100 million years. The universe is not a place we are looking at. It is a delivery still in progress, and every sentence of cosmology has been written from what has landed so far. Which means the reconstructed history of the universe rests on the same assumption as your recollection of yesterday morning. Not a similar assumption, the identical one. That records are traces of events, rather than arrangements that simply exist. And that assumption cannot be established from the physics. It has to be chosen. So the timeline, 14 billion years, the first structures forming, the first stars igniting, galaxies assembling, the elements in your body forged inside dying suns. Every stage of it is read off objects that exist today, conditioned on a moment that nothing in the mathematics selects for us. There is one record older than all the others, the faint light left over from the universe's first transparent moment, still arriving from every direction at once, in every part of the sky, at every hour of the day. It is the deepest the doubt can reach, and it reaches it. Not because there is anything wrong with the measurement, because it is a record, and that is the only qualification the problem requires. Now the necessary restraint, because this is exactly where the argument gets abused. None of this means astronomy is wrong. The measurements are good. The reasoning built on them is careful, cross-checked, and internally consistent to a degree that is genuinely remarkable. Nothing in the 2025 paper suggests a single number in cosmology needs revising, and not one of the three authors has ever hinted at such a thing. The claim is narrower and far stranger. It is that astronomy, exactly like memory, runs on an assumption it cannot supply for itself. It works. It has always worked, and its foundation is a choice rather than a result. A tool can be reliable without being self-justifying. Those are two different properties, and physics has spent 200 years quietly treating them as one, which explains the title of this film. State it carefully, because it is easy to hear as something more dramatic than it is. Physics has not been proving your past. It never claimed to be. For 2 centuries it has been assuming it, productively, with spectacular results, and that assumption has not once let anybody down. But an assumption that always works is still an assumption. The past hypothesis is not a discovery about the universe. It is the condition that must be granted before discoveries about the universe can begin. Which leaves you with a single question, and physics has now handed it back. If the mathematics cannot decide whether your life happened, what can?
Mathematics has a boundary, and it is not where most people imagine it. The limit is not complexity, not the size of the calculation, or the power of the machine, or the cleverness of the physicist. The limit is that a formal system can tell you what follows from an assumption, and it cannot tell you which assumption to make. That is not a failure of physics. It is the shape of physics. This is not a peculiarity of the entropy problem either. Every theory ever built has the same structure. Newton's laws tell you how a body moves once you have specified where it started and how fast it was going. They are silent about where it started. Relativity will describe how space-time evolves from a given configuration and says nothing whatever about which configuration. Physics has always been a machine that requires an input it cannot generate. So when the 3 authors reach the end of their paper, they do not produce a resolution. They point outside. The choice of moment, they say, has to arrive from somewhere other than the mathematics, from prior belief, from judgment about which assumptions are worth holding,
from reasoning about probability that begins before the physics does, which sounds like a surrender. It is not. It is the most honest sentence in the paper, and it opens the only door out. That door was found in the year 2000 by the same philosopher who named the past hypothesis. David Albert noticed something about the fluctuation scenario that nobody had properly stated. The problem with it is not that it is false. The problem is that it cannot be believed. Follow it through carefully. Suppose you accept it. Suppose you conclude that you are a momentary arrangement and that your memories are not records of anything at all. Now ask what you used to get there. You used your understanding of statistical mechanics, which you learned, which is a memory. You used your recollection of the argument as it was laid out, step by step, over the last hour, also a memory. You used your confidence that the words you heard were really spoken, that the numbers quoted were real, that a paper exists, that 3 physicists wrote it. Every one of those is a record. And the conclusion you have just accepted says that records cannot be trusted. So the hypothesis eats its own justification. If it is true, you have no grounds for believing it, because the entire chain of reasoning that delivered you to it is built out of exactly the material it declares unreliable. Accept it, and you must immediately discard the reasoning that produced it. Discard the reasoning, and nothing supports accepting it. Put it at its sharpest. If the hypothesis is true, the paper described in this film probably does not exist. There are no 3 physicists. There is no journal, no server, no December. The impression of having encountered an argument is simply part of the arrangement, no more connected to a real argument than a dream is connected to a real room. Albert called this cognitive instability. Sean Carroll took it up and pressed it harder, and it is now the most widely held answer to the whole problem. Notice carefully what it does and does not accomplish, because that distinction is everything. It does not prove the hypothesis wrong. There is no refutation here. The idea remains permitted by the mathematics, exactly as permitted as it was an hour ago. What it establishes is that the hypothesis is unusable. It cannot be held as a belief without dismantling itself. It generates no predictions. It licenses no actions. It cannot even underwrite confidence in the argument that produced it. Not false. Unlivable. This is not universally accepted, and it would be dishonest to present it as closed. There is formal work on both sides. Some physicists argue that with proper Bayesian conditioning, the problem dissolves entirely, and that the fluctuation hypothesis is defeated by the mathematics rather than by its own instability. Others hold that cognitive instability is doing real work, but is not quite the clean kill it appears to be. The dispute is live, technical, and being conducted by serious people right now. But the shape of the answer is agreed on, even among those arguing about the details. Whatever finally settles this question, it will not be an observation. It will be a decision about what a reasonable mind should assume before it begins. So here is where all of this actually leaves you. You cannot prove your past happened. You never could. That was true before this film started, and it will be true tomorrow. And no experiment will ever alter it, because every experiment is made of the thing in question. What you can do is notice what the alternative offers. It offers no predictions. It tells you nothing about what happens next. It gives you no reason to act one way rather than another. It cannot support the science it was derived from. It cannot sustain belief in itself. Set against that, trusting your memory is not a leap of faith, and it is not naivete. It is the minimum assumption required for anything to be thinkable at all. It is not a conclusion physics arrived at. It is the ground physics has to be standing on before it can arrive anywhere. You were never given proof that your life happened. You were given something more fundamental than proof, and a great deal less comfortable. You were given the only assumption under which the question can be asked. Which brings us back to the star. Betelgeuse is out there, in the shoulder of Orion, burning orange while the stars around it burn white. Or it is not there at all, and has not been for centuries, and the light still arriving is the last of a message from something that ended before anyone now alive was born. An hour has passed, and nothing about that has been resolved. Nothing about it can be resolved. Not tonight, not this century. The information required is in transit, and it will not land for another 600 years. But something has changed, and it is not about the star. At the beginning, that uncertainty looked like a curiosity, a quirk of distance, an interesting problem belonging to astronomy and to nothing else. It was never a fact about Betelgeuse. It is the condition of every record in the universe, including the one reading this sentence. So find it one more time, and this time, name it exactly. Not a star, not an illusion either. A record, arriving, accurate, and completely silent on the only question you actually want answered. Physics has taken you as far as it goes. It explained why time has a direction, and how that direction rests on nothing but counting, and how the counting permits almost anything, and how the reassurance that satisfied everyone for a century was standing on itself the entire time. And then it handed the question back, unanswered, the way it was always going to. Physics cannot prove your past was real. It never could. It only ever assumed it, and then built everything else on top.